I'm going to talk about the highly riveting topic of food packaging safety and regulatory compliance. Going to go through how to make a determination basically of whether or not your product is safe. So with flexible packaging, we're seeing several trends. Consumers today, they want something fast, they want something on the go, they want something ready to eat. You know, it's that on-the-go lifestyle. But at the same time, we're looking at people who are also concerned about migration. We've heard of bisphenol A getting into your food. We've heard of ITX in Italy. So, I mean, there's a concern about the safety of packaging. Brand owners, similarly, are also concerned about this. They don't want any recalls because the package is unsafe. So they want to understand what could possibly go into their food, into their package, and what's coming from the suppliers of that. Again, they want our assurance that what we're handing them is something safe and suitable for what they're using. And the converters want the same sort of thing. But at the same time, there's this other demand where they want things cheaper, they want to be able to move faster, and they want cost and production efficiencies. So I'm going to talk about the regulatory and compliance part of this and the food safety and how Ashland approaches this. And Ashland, I don't know, we are a very diverse chemical company. The group I'm in, we do adhesives and coatings for the most part. I'm going to focus on the adhesive side of it, mainly for some of the work that we have done, and give you an idea of what our approach to this has been. So for the US, there are two regulations with which we have main concerns about for adhesives. One is 175-105, this is an FDA regulation. This is essentially the room temperature adhesive regulation, even though it doesn't have a temperature compliance part of it. And this assumes that the adhesive is separated from the food by a functional barrier. Now, what does this functional barrier do? It's supposed to prevent migration. And what does that mean? We'll get into that later, but there's various definitions of that. The other one that we have concerned about is 177-1395. This is for a laminate structure. This does not assume that the structure acts as a functional barrier, but the adhesive will actually migrate. The weird thing about this regulation, the adhesives that are listed in there, for the ones that are used on the market today, they don't really compositionally comply. There's a lot of different components in these products now, and none of them are really listed. So how does an adhesive manufacturer make it a compliance determination? Well, there's ways to do that. Some can assume that there's a functional barrier, it's not going to migrate. Probably not the safest way to do that. Or you can actually do migration testing in the proper food simulants with times and temperatures and conditions and that sort of thing. The key to both of these regulations, however, is that the adhesive cannot adversely affect the food. You can't simply rely on a compositional listing and assume it's safe. You basically have to know that that functional barrier works. So you cannot compromise safety or the taste or composition of the food due to some sort of migration issue. And how do we do this? The FDA and the European Food Safety Association have provided guidances for migration. I'm going to focus on the US FDA, but both of them are fairly similar. They provide guidance as far as how to do the testing, what temperatures to use, what types of food simulants to use. And using these guidelines, we are able to safely determine whether or not our product is safe for the intended use. Now, there are three components to this. You really need to understand the package. What type of food is going into it? The type of food can greatly determine how a product will migrate. Also, what are the conditions? The higher the temperature, the more migration you're going to see. How long is it going to sit on the shelf? Again, that will enhance migration. So you have migration. What does it mean? What's coming out? You have to perform a risk assessment on those chemicals that have migrated to determine if they are safe at that dietary level that you anticipate. Okay, so in the FDA's chemistry guidelines, they have listed basically 4 food types based on their migration potential. Aqueous and acidic foods, which would be your fruits and vegetables, condiments, milk and bread are also in there. Alcohol foods, you know, typical beer, ale, and wine. And for flexible packaging, these are like those adult juice pouches, but with alcohol in them. Kind of cool. Then fatty foods. And the majority of the flexible packaging that we see is this type of package. So cheese, butter, meats, potato chips, cookies, that sort of thing would be considered fatty food because they have oil on their outer surface. And then dry foods. The dry foods is fairly limited. I mean, it truly means a dry food. Uncooked pasta with nothing on it, dry cereals, rice cakes with no flavoring on it, coffee that's non-flavored. It's a very, very small group according to FDA. Now for each of those groups, you have a food simulant, a way to simulate that food specific to that food type. So for aqueous and acidic foods, you have 10% ethanol. For alcoholic beverages, it's 10% ethanol unless the alcohol content is higher, and then you bump up the ethanol content. Fatty foods, they recommend 95% ethanol. And then for dry foods, there's really nothing specified right now. There's some talk of using a chemical called Kennax, which is a dry powder, but nothing's come of that as of yet. Now doing testing in these is critical because those food simulants greatly change how migration occurs. And in the next slides I'm going to show you is basically the effect of migration the food simulant has on it. The chemical we're looking at is aromatic isocyanate. This is a chemical used in many laminating adhesives. It's very common. The problem with aromatic isocyanate is it will migrate, it'll hit water and turns into aromatic amine. And aromatic amines are carcinogenic. So there's a great concern around this, even though these things are very commonly used. The migration around them needs to be understood. All right. So for this test, we have this typical aromatic isocyanated adhesive. We have cured the material for 2, 3, and 7 days. We have 2 food simulants. They've both been tested for 2 hours at 70 degrees C on a 1 mil linear low density polyethylene. So a very common barrier film that they would use. Very thin, not a very good barrier for most applications, but it's fairly common. We tested in 3% acetic acid, which is our aqueous food simulant. I know I said 10% ethanol is what FDA recommends, but you can also use 3% acetic acid, and we've seen equivalency between the two, so we're using 3%. The other food simulant we use is the fatty food simulant, 95% ethanol. As you can see, migration in 2 days is greatly different between the two. After a 3-day cure, it's still pretty large, and at 7 days cure, it's fairly similar. So the issue is, when are you going to put food in this package? If it's a fatty food, you really need to wait for that material to cure. And if you're using a fatty food, do you really want to be testing an acetic acid when you see this great of a difference in migration? So if you're using acetic acid versus 95% ethanol for a fatty food, you're greatly underestimating the exposure to, in this case, aromatic isocyanate and the potential risk for cancer. So that's the food simulant. The other part of this is, what are the conditions? The FDA has listed in its chemistry guidelines various conditions for the proper testing. For instance, condition E there is room temperature. So this would be a bag of chips sitting on a shelf. There's no heat treatment to that. For that test, you would test it 10 days at 40 degrees Celsius. Another common one is condition use H. This is for a pre-cooked food that you would throw into a microwave for like 15 minutes. This is a 2-hour test at 100 degrees C. You would test at that condition. And then you have various conditions of hot fill and retort, where these higher end ones. So boiling water sterilized, you test it 2 hours at 100 degrees Celsius, followed by 10 days at 40 degrees C. In that case, you get the hot fill condition of it, or the heat treatment, and then you also get the shelf life of that. So using, again, the same adhesive and the same cures, the only difference here is we're using a 3 mil linear low density polyethylene. So it's a thicker film, so we should see less migration. The two conditions are that condition to use E, which is room temperature. That's at 10 days at 40 degrees Celsius. The middle column is condition to use H, which is that pre-cooked food, 100 degrees C for 2 hours. And then a hot fill with extended shelf life, that was 100 degrees C, followed by 4 days at 40 degrees Celsius. And you can see, depending on when you cure it, the migration greatly changes. So between the room temperature condition and the hot fill condition, you can see how much migration increases. But then if you add shelf life component to it, you have even more migration. So again, depending on how you do this test, and depending on what your conditions are, you need to get a good idea of how much your material will migrate under realistic conditions. If you're only doing room temperature testing and you have a hot fill application, you're going to underestimate that exposure. All right. So what's a functional barrier? you look at the definition, it's going to be anything that prevents the migration of the non-food contact material into the food. So in this case, our adhesive. It could be a coating on the outside of a film. Anything where it's not actually touching the food would be going through a functional barrier. So what's acceptable as far as this definition? A lawyer might tell you 0. Well, if you have anything to do with analytical chemistry, 0 is more of a concept, not a real definition. Eventually, we're going to be able to detect it at low enough levels where you're going to see it. 50 part per billion is often thrown out there also. I don't know where this came in, but again, this may work for certain chemicals, but for a carcinogen or a reproductive toxin, that may not be a low enough level. Or you could look at it as far as below the level of risk. And what I mean by this is you have a chemical that causes a certain amount of hazard, a certain level in the diet which is harmful, a certain amount of exposure. Are you below that risk level where those two multiplied together? Are you safe below that level? And this is the approach that Ashland takes, is looking at doing this. We are trying to get below that level of risk. Now, as far as what is a functional barrier, are there any definitions out there? As far as actual films, not really. The FDA and EU have not really come out with anything. The FDA has come out with some for PET, 1 and 2 mils of PET. They've said some things about glass and metal, but for the most part, there are no real definitions out there saying, oh yes, if we use this, then we're safe. Which is a real problem because it's the food packing manufacturer's responsibility to make sure that their barrier is indeed functional. The only real way I think you can do this is with data. So on the next bit of slides, we've been in the process of developing a low migrating adhesive, one that migrates low aromatic isocyanate. We got into this, we had no real idea of what these barriers would do, so we wanted to test them. And so the next slide you're going to see is what the effect a functional barrier has on migration of aromatic isocyanate. So we have a 1, 2, 3, and 4 day of cure. And right now, if we just compare the linear low density polyethylene, those first 2 columns, we didn't do 1 and 2 days. I mean, if there's a slash there, it means we didn't test at that because we had an idea at the time that it wasn't going to work. But if you look, 3 mil at 4 days is better than 1 mil. Makes sense. It's thicker. You're going to prevent that migration. Then if you go to the other 2 columns there, this is a 4 mil and 2.25 mil 7-layer mixture of linear low density polyethylene and EVOH. Now EVOH is considered a really good barrier, and we were expecting not to see any migration. But it doesn't appear to be any different than the linear low density, the 1 and 3 mil. What we do see is a difference between the 4 mil and 2.25 mil because of their thickness. But no, we couldn't draw a real conclusion between a 7-layer versus a single layer. And again, all these were tested at 2 hours at 100 degrees C and followed by the shelf life testing. So the next one, we're looking at 2 other films. The 3.5 and 2 mil high density polyethylene. We didn't see any migration of aromatic isocyanate with a 3.5 mil HDPE. However, just decreasing that thickness slightly, the migration was very high at 1 and 2 days. So again, you think, oh, at 2 mil I might be safe. It didn't happen. Now here's the next 2 are just. This was really interesting as far as what we were thinking. The 1.5 mil 3-layer EVA, with HDPE, we expected to be a very good barrier. The migration of aromatic isocyanate was off the charts. I mean, these are well above any risk level. Why is this happening? We don't know at this point. But again, what we expected, based on what we've heard about EVA being a good barrier, and what we saw from the HDP and the other 2 columns there, it didn't happen. The next one is this 1.5 mil metallized film. This is actually a film that looks like metal. The migration was outrageous on this one. Very high levels. We would never have seen anywhere where we'd ever comply with it. What happened with this? Well, there wasn't anything wrong with the structure itself. We looked under electron micrograph and looked at the metallization, and even though it looked like it was perfectly clear, like just a straight sheet of metal, it was spots of metal here and here, but to the eye it looks like it's great. So we're thinking that when the metallization process occurred, it actually damaged the barrier and it wasn't a complete coverage, so the migration was that much higher. It actually ate away at the linear low density polyethylene. So again, it may have looked like a barrier, but it certainly wasn't. So just a word of caution when you're thinking about barrier films. So not all barriers are created equal. They don't have equal functionality. And it's really hard, other than thickness maybe, to get an idea of, is this barrier actually functional? You can't easily predict them. You know, mixtures of films may change the barrier properties from what we can tell. It's just one of these things where we have to have more data to understand this better. Another potential is we're using ethanol as our food simulant. Was this overly aggressive? Was it able to work through the film easier on some of these films and pull out the aromatic isocyanate? Next PackExpo we'll have data on that. We're going to test in some actual food oils and some different simulants also to see if that was an effect. And the question needs to be asked though, do we have to test all of these film, food, and conditions for every type of barrier structure out there? I don't know yet. I mean, you've seen the data. I think you might be able to make some predictions based on classes of data, based on classes of film, but you can't go from one film type to another and assume that that's going to be a better barrier than another. All right. So what does all this mean? You got a number spitting off a machine, says it's this level coming off the package. What does it mean? Well, you need to be compared to a dietary level, that's something that's safe. In the European Union, they have a thing called a specific migration limit. There's, I don't know, several hundred of these listed in their plastic implementing measure. It doesn't contain all of them, so some of them aren't going to be listed, but if you meet that requirement, then you can say, oh yeah, this is safe for use for that particular analyte. The US FDA does not have these. They are, and they're unlikely to recognize them either. They're very risk-based. They want you to show how much exposure there is to the package, what the component is as far as understanding the hazard. They're not going to accept the European specific migration limit if you went to them and said, oh, we're good for Europe. Well, that's great, you're good for Europe, but not in the US. So, what do you do when you don't have this information? How do you evaluate a chemical which does not have pre-market clearance? For a chemical that's not listed by FDA or EU, what do you do? Luckily, the FDA and the EU have recognized this. Under Article 3 of the Framework Regulation, the EU, they basically say, if you can demonstrate that this material is safe for ingestion, it doesn't cause a change to the taste and odor of the food, then you can determine it's safe even if it doesn't have a listing. In Section 402A of the Federal Food, Drug, and Cosmetic Act, the FDA basically says the same thing, saying, as long as your product does not adulterate the food, you're good. Again, that means safety, taste, and odor, and composition. So this comes down to where you hire your toxicologist and you do risk assessments of the analytes that are coming off of your package. Now, I put this at the end of my talk because it just flowed better, but you actually will probably want to do this work before you get into migration testing, because then you can tell your chemist this is your detection limit, this is what you have to do. So, but again, this is how you go through this. Do it up front though. So what you want to do is look at the potential migrants coming off your package and determine a safe dietary level for them. If you have a chronic study in rats, let's say, and you have a material that is shown to be safe, a no observed effect level is what that is. Any toxicologists out there? Yeah, we're rare. No, you are? No, you're just yawning. Yeah, I do too, even at toxicology. Anyway, what you do is you take that no observed effect level and you divide it by 100 and you get a safe dietary level. These levels, you know, it could, if you have less data, you have to put more of an uncertainty factor on, so maybe 1,000-fold less than that number that you saw. There's different ways to do this based on risk assessment practices. That's why you need to get with your toxicologist to set these levels prior to doing the migration testing. The other part of this is determining the exposure of your package in the marketplace. How much of the diet is exposed to that particular package? We've done some work, flexible packaging, depending on the geography, it could be 3 up to 12% is what we're seeing. Your diet maybe has something in a flexible package. And you can use that value to do your risk assessment. The FDA in their chemistry guidance also has these default exposure levels. They're called consumption factors. So for an adhesive, I believe it's 14% of your diet has some sort of product containing an adhesive in it. If it's a polyolefin, I think it's 35% of your diet's in a polyolefin type packaging. So they do have these exposure values in there. The problem with them is they were written back in 2000. The packaging market's changed since then. They may not be accurate, and they may cause overexposure or underexposure. Well, anyway, if you take that safe dietary level, that top bullet there, and you divide it by your exposure, you can get your detection limit. So if you have, let's say a safe dietary level of, 50 parts per billion, and you have a 5% exposure, just divide it by that, and you'll get your detection limit. In this way, rather than relying on a specific migration limit or relying on the assessment of somebody else, you have been able to determine if your package is safe based on the migration, level coming off, and the hazard of that material. So what do you do if there's no toxicity data? There's no toxicological data. There's a lot of chemicals out there that are used in food packaging which have no data on them. Well, you could do read across to structure analogs. So if it's an acrylate-based chemistry and you find something fairly similar, what's that product look like as far as its toxicity? Can we do the same thing for this one? That's perfectly acceptable. Again, probably want to make certain, you may even want to add a little more uncertainty to that as far as the safe level you come up with, because it's not a direct comparison. The other thing you can do is testing. The testing can get very expensive, as many of you probably know. If you're doing genotoxicity testing, you're probably looking at $20,000, $30,000 up front. If you have to get the subchronic toxicity, you're getting to several $100,000 up to millions of dollars. So what type of data do you need? Well, that depends on the dietary level. In the FDA and their toxicity guidance, a level of 0.5 parts per billion in the diet, I'm not talking detection limit, I'm talking how much you actually ingest. They don't require any data at all. They're basically saying that's so low that it's below the threshold of regulation. It's not in our wheelhouse, essentially what they're saying. Provided that it doesn't have any evidence of carcinogenicity. So if there's a structure analog of what you're looking at and it has a cancer study on it, you can't rely on this 0.5 part per billion. At 0.5 parts per billion to 50 parts per billion in the diet, you're looking at 2 in vitro, so test tube determinations for genotoxicity. So test in bacteria, the mouse lymphoma assay, chromosomal aberration. That's the type of testing you're looking at. Again, you're looking at that $20,000 to $30,000 range in testing. Above 50 parts per billion in the diet, up to 1 part per million, this is where you're doing genotoxicity. You're doing those 2 in vitro tests. You're also doing an in vivo genotoxicity test, so you're actually injecting a mouse, seeing if it causes DNA damage. And you're also doing 2 subchronic toxicity tests in mammals. And this is where the money comes in, because this is a 90-day test in a rat, 2 mammal species, probably a rat and a mouse, I would assume. Those are going to be several $100,000. It may say 90 days on to get this done. You're looking at a year and a half, 2 years before it's completed. So if it's not been evaluated by FDA and you can't find a good structural analog, you might want to try and keep your exposures below or find a different product to put in there that has data on it, because this gets very expensive at that point. All right. So to recap our approach to food safety, we want to determine all the components that may migrate from the package. And using the appropriate and realistic toxicological data, establish a safe dietary level using those. Then we want to apply actual exposure data to that to determine the level of risk. We're going to perform all this in the proper food simulants according to the proper conditions based on the food package, the food packaging conditions. And this is the key to this. If somebody says, I need this type of package, you need to know, this question you should be asking, okay, what food's going into it? How's it going to be processed? How long is it going to sit on the shelf? Those are the questions you need to ask up front. So you really need, this is where the key is between people like Ashland, our converters, and the brand owners. It all needs to be a discussion about what are you doing with this so that we can provide a better product and a safer product for you. So once you've done all that and you've done your testing, you assess the package for its intended use. If all your numbers are below that detection limit that you set based on the risk and the dietary level, you're good to go. You can make a safety determination. So with that, I think all I have is a legal disclaimer, which I'm not going to read, and I'll take any questions. Thank you.